Hi, welcome to my channel, JaberTime. Today I'm going to go over parametric surfaces and their area. Let's get into it. For parametric surfaces and their area, we're going from U and V plane to a three-dimensional X, Y, and Z. We can describe a surface by a vector function R, U, and V of two parameters U and V. I'm trying to stay focused with you. As you could see, guys, a lot of notes, but everything is highlighted and colored, the ones or the key terms that I wanted to stay focused with me. And I'm trying not to go off topic by staying focused with the notes. That's why I feel like my most of my lecture videos, I'm just trying to be formal and sticking to the notes. Trying to not to make it 45 minutes, and hopefully it won't be 45 minutes. So let's stay focused and follow me. R, U, and V to point to any point on the surface will be of the components X and Y and Z of U and V, where X is a function of U and V, and Y is a function of U and V, and Z is a function of U and V. So those parameters U and V are the main part. You have to focus on that you have three variables or three components, but they're coming from two. Kind of hard to think like, single variable calculus. We go from X to Y. Here we have X and Y going to X and Y and Z. Kind of like, from 2 to 3. So my domain is a plane and my range is a three-dimensional. The component functions of R are functions of two variables. In general, we call them U and V, where U and V are called the parameters. You could see circled, boxed. Those are things that are very important for this video that you need to pay attention to. Find a parametric representation of the sphere x squared plus y squared plus z squared equals a squared. The sphere is simply rho equals a because the radius is a. So let's choose the angles phi and theta as the parameters. So as theta and phi changes, I will be moving along or around the surface of the sphere, and I will cover it all. The main thing is your parameters. You need to identify them and take care of them clearly, phi and theta, where x depends on phi and theta, and so on and so on. Those are my components, but they depend on phi and theta. Phi goes from 0 to pi, and theta goes from 0 to 2 pi, and any point on the sphere could be represented by r of phi and theta, which is a sine phi cosine theta I plus a sine phi sine theta j plus a cosine phi k. So the parameter domain is a rectangle. So this is my domain. Those are my restrictions. As theta changes and phi changes, this is theta and this is phi and this is theta, I will be moving around the sphere. Let me quickly highlight that for you. I have the notes right here, so I'll keep it for you and I'll go through it while it's written. Here we go. The grid curves with phi being constant. This is phi equals c. So going from the positive z-axis with a length or the value of phi, staying here, you will see a circle right there. Are the circles of constant latitude, including the equator. So when phi is fixed, you're going to deal with circles around this way. Where on the other hand, when theta is constant, that's when theta is constant like k, you're gonna deal with a semicircle. You see this semicircle is not going the other way, because theta will change from 0 to 2 pi. You're gonna cover them all the semicircles, or the sphere being with semicircles. So this line right here will be traced as this semicircle. This line right here will be traced as a circle. See, the circle is going around with the dashed lines in blue. You could see that. Okay. Find a parametric representation of the cylinder. X squared plus y squared equals 4, where z goes from 0 to 1. So we have a cylinder with a radius of 2, but has an end. Of course, it's not going all the way up from 0, from the xy plane up to the surface or the plane z equals 1. To rewrite this with parameters, notice that r equals 2 is fixed. The cylinder has a simple representation, which is r equals 2. In cylindrical coordinates, we have the following. So we have theta and z as parameters in cylindrical coordinates. Once I know theta and I know how far I'm going up z value, I will be tracing the cylinder and will be covering the whole cylinder. So the focus now is what are the parameters in each problem. In this problem, it's theta and z. Then the parametric equations of the cylinder are x equals 2 cosine theta, because r is 2. Y equals 2 sine theta. And z equals z. That's how we use the cylindrical coordinates, where theta goes from 0 to 2 pi and z goes from 0 to 1. Find a parametric representation for the surface z equals 2 square root of x squared plus y squared, that is the top half of the cone, where z squared equals 4x squared plus 4y squared. If we regard x and y as parameters, then the parametric equations are simply a point xyz on the cone satisfies the following. My parameters are x and y, so I'm going to keep x as x, I'm going to keep y as y, and z depends on x and y. This is how we think about parameters. It doesn't have to be always phi and theta or u and v. In this case, we could see clearly as we are tracing, walking on the cone, the top half, as x changes and y changes, we are at a z value, which is 2 square root of x squared plus y squared. And the vector equation is xi plus yj plus 2 square root of x squared plus y squared k. Here's another way to represent the cone that we have. Could use polar form or polar coordinates. In this case, the parameters are not going to be called x and y, they're going to be called r and theta. A point xyz on the cone satisfies the following. X equals r cosine, y equals r sine theta, and z equals 2 square root of x squared plus y squared. We're going to call it 2r because we're not going to speak x and y. And the vector equation is r of r and theta. This is r as a vector, this is r as a radius, theta that we are familiar with. So we have r cosine and r sine and 2r, such that r is greater than or equal to 0 and theta goes from 0 to 2 pi. Now, tangent planes. This connects us to the kind of like the fourth video maybe, or the fifth video of the playlist of this section, vector calculus. But now we're in space and we're dealing it a little bit differently. But instead of skipping this example and this introduction, let's go over it a little bit quick. Of course, you could visit and come back and see it more in detail by slowing me down by hitting the spacebar. Here we go. Now we have a parametric mode. We have u and v going to x, y, and z. We now find the tangent plane to a parametric surface S traced out by the vector function ru and v equals x of u and v I plus y of u and v j plus z of u and v k. At the point p sub 0, this is the point p sub 0. Alright? Notice that before I move on and read for you, I'm boxing this right here, I'm circling this right here for you, and I'm underlining this for you. So stay focused with me so I could make it more clear from the graph. If we keep u constant, u being constant, that means I am on this line. That's u equals u sub 0. Then r of u sub 0 v, as you are pointing here, a vector function of the single variable v. V changes and u is being fixed. And defines a grid curve C1. This is C1. It's kind of hard to see, but this is C1. And on the other hand, you could see C2, so you could see the concept of C1 and C2. Here's C2 coming after this nodes. C2 goes this way. And C1 is going this way. Why this is happening? Because we are fixing u to be u sub 0 and v changes. So we're kind of like moving in one direction, tracing where the values of v changes but not u. The tangent vector to C1 at this point p sub 0 is obtained by taking a partial derivative of r, of course with respect to v, because u is constant. As you could see, it's a little bit small to look at, and my idea is like I try my best to write all the notes in one slide instead of clicking and skipping steps and steps. It's kind of hard, you forget what I started with. So this is rv. Since as you move this way on the surface, when u equals u sub 0, v changes. Now partial derivative with respect to v will be the tangent vector. And if you want to put p sub 0 like you mean at v sub 0, that will be at that location. So rv is the partial derivative of r with respect to v. dx dv, dy dv, dz dv. U sub 0 is fixed, u sub 0 is fixed, u sub 0 is a fixed amount. If you want the tangent vector at this point, you put v sub 0 and v sub 0 and v sub 0. Okay? We are finding derivative with respect to v, then we plug in v sub 0. Let's move the other way around. Notice now I'm boxing this right here, and I'm referring to this right here, which is ru, the partial derivative of r with respect to u. Before you do that, we are tracing along the curve C2. Here's the notes, excuse me. Similarly, if we keep v as a constant, v equals v sub 0, by putting v equals v sub 0, we get a grid curve C2 right there, given by r of u and v sub 0 that lies on the surface S. The tangent vector at p sub 0 in this case is the partial derivative with respect to u, because u is the variable. dx du, dy du, dz du. V was fixed, but now after we find the derivative, we plug in u sub 0, u sub 0, u sub 0. Now we understand what's happening here and what the tangent planes are going to do for us, or tangent vectors at p sub 0. I'm thinking about the tangent plane. If the cross product is not 0, then the surface S is called smooth. It has no corners. Kind of like a simple concept from calculus 1. When we say smooth, means like has derivatives. Curvy as smooth polynomial. For a smooth surface, the tangent plane is the plane that contains the tangent vectors Ru and Rv. Partial derivative with respect to u, that's this one here, and partial derivative with respect to v, that's called tangent vectors at this point p sub 0. And the vector, which is a cross product of these two vectors, will stick out, will be out. If you remember the right hand rule, that will be a normal to those two vectors, to the tangent plane, because the tangent plane here will hold or will contain those two tangent vectors. Let's go back. Those are the concepts that we need to use for the tangent plane. So when we find the tangent vectors at this point, we do the cross product, we get the normal, and we need the normal for the plane equation, which is in our case is called tangent plane. Find the tangent plane to the surface with parametric equations x equals u squared, y equals v squared, and z equals u plus 2v at the point 1, 1, 3. We first compute the tangent vectors. That's called the partial derivative of r with respect to u. Dx du will be 2u, dx dy du will be 0, dz du will be 1. Okay? We're gonna do now what? R, v, partial derivative of r with respect to v. The last one with respect to v is 2. You could see that. What do we do next? We need to find the normal, which is a cross product. The normal vector to the tangent plane is the cross product. I'm using colors to let you stay focused. This goes on the first line right here. This is kind of like the title line. And this goes on the second line. 2vj, 2v, 2 for the k, and 0 for the I. Doing the cross, you get the following. Since x equals u squared, and y equals v squared, and z equals u plus 2v, notice that having the point 1, 1, 3, 1 for x, 1 for y, and 3 for z will lead me to u equals 1 and v equals 1, and that should do it. Now we know u and v instead of the concept of 1, 1, 3. Why do I need it? Because of the following. So the normal speaks about v and u. I need the values. I need the normal at that location, because the normal changes angle on a surface. But at that point p sub 0, which is 1, 1, 3, the normal will be when I plug in 1 for u and 1 for v. Doing the math, I have minus 2i minus 4j plus 4k. Let's summarize this problem. Therefore, an equation of the tangent plane at 1, 1, 3 is, remember those comes from the normal, That's my normal. And I'm using different color for the point x minus x1, y minus y1, and z minus z1. Simplify this, I get x plus 2y minus 2z plus 3 equals 0. That should do it for this problem. And let's move on. Surface area. This right here, I could skip the whole thing and give you the definition which comes after this. But I'm trying to keep my notes consistent with each lecture notes with examples. I'll go a little bit fast right here, but you get the concept, you get the idea, trust me. Here we go. So if you feel like I'm going a little bit fast, you should know why. Because I want to get you to the formula, but I want you to believe in the formula. For simplicity, we start by considering a surface whose parameter domain D is a rectangle. That's the easiest way that we could start with. And we divide it into subrectangles R sub ij. This whole portion, I know it's small to look at, but you get the concept. So we are looking at a sample, which is a rectangle, and we are going with the vector R from our domain, the parameters R, U, and V, to the space XYZ. This will be mapped to this blue portion. Let's choose U sub I star and V J star. Remember, like Riemann sum, when we take midpoint and right and left and so on. So we're taking the kind of like the bottom left point of each rectangle. Be the lower left corner of Rij for each Rij. Now this portion right here, it's down here. That's Sij. The part Sij of the surface S that corresponds to Rij is called a patch and has the point Pij, this point right here, this point right there, with position vector R, U sub I star, V sub j star, because it's coming from this point, as one of its corners. Let Ru star, which is the partial derivative of R with respect to U, at that location, be Ru Ui star V j star. And let's the partial derivative of R with respect to V at that point be Rv star. That's why it's called star, because it's coming from this point. That was called U I star and V j star. So that will be the partial derivative with respect to V at that location. Be the tangent vectors at this point Pij. Pointing to this point, position vector will be called R. Doing Rv and Ri, that means I'm doing the tangent vectors. Now, if you want this right here, not just a tangent vector all the way, the two edges of the patch, that meet at Pij can be approximated by vectors. These vectors, those are the vectors that we are referring to. You see the arrows right there? Can be approximated by the two vectors delta Ui Ru star, that's this one right here, and delta Vj times Rv star. So this vector and this vector. Notice that this is a gray parallelogram. It's part of the surface plane to the surface blue graph. We have a tangent plane. I don't know if I call it surface plane. We have a tangent plane being in gray, and that portion will be covering that patch below it, because we are taking not Ru star, we're taking Ru star times delta U. So we approximate Sij, this part is Ij, this part is Ij, by the parallelogram determined by the vectors as a cross product, if you remember from earlier videos in this playlist. By doing the cross product, we simplify this to the following. And this is exactly what we want. And so an approximation to the area of the whole S, not just only this patch, will be the summation. We're going to do the Riemann sum. I goes from 1 to m and j goes from 1 to n of the whole package. Now the final point, which brings us to the definition. This is a little bit small still, looking at the slide, but I want to summarize this whole page for you. As I said, I could just give you the definition without any explanation, but I think you benefit from seeing some details and some graphs. Here we go. Definition. If a smooth parametric surface S is given by the equation x of u and v equals, that's capital X or v, x equals u and v equals plus y of u and v j plus z of u and v k, where u and v belongs to d, and S is covered just once as u and v ranges through the parametric domain d, then the surface area of the surface S is, that's the surface area. Notice here there is 1. There is no f of x, y, z. You do the cross product between the partial derivatives of u of r with respect to u and r with respect to v. And if you need to know more details, how do you get those parts? That's how you do it. And you know how to do the cross product now. We have seen some examples and that should do it. This is, as I said, I don't want to skip it, but this is something basic or major that you want to keep with you. Find the surface area of a sphere of radius a. Well, we know the surface area of a sphere with radius r as a formula. It's called 4 pi r square. So let's find this one here, and hopefully we end up with what we should expect, which is 4 pi a square. Let's get started. From the first example, we found the parametric representation of a sphere using the parameters phi and theta as follows. Instead of reading the whole thing, guys, you believe me, we have seen this before, so I'm trying to read less and save you some time. We first compute the cross product of what? Usually we call it RU cross RV. In this case, that's not U and V, it's called phi and theta. That's the cross product. dx d phi, dy d phi, dz d phi on the first line, and on the second line will be the partial derivative of r with respect to theta, which is dx d theta, dy d theta, dz d theta. Doing the math, knowing what's x, knowing what's y, knowing what's z, this is what you have. I'll just verify the quick one, the last two parts. Here we go. What is dz d phi? Well, I have a cosine phi, and the derivative of cosine is negative, so I'm going to end up with minus a sine phi. What is the derivative of z with respect to theta? There is no theta in it, so it's going to be 0. So, finishing the determinant, which is a cross product of r phi and r theta. I'm slowing down reading, but I give you some time to look at it. Once you're done, we need the magnitude, because the magnitude will give me the area. The magnitude of the cross product is the area of the vectors being formed on the plane before the cross product. So how do you find the magnitude? You square each part and you add them up and you put the square root. Now, to simplify the algebra for you, I have blue, green, and black. Looking at the blue parts, a to the 4 sine to the 4 phi, a to the 4 sine to the 4 phi. I'm going to take those out as a common factor. You can see that. From the first, I have cosine squared theta. From the second, I have sine squared theta, which actually equals 1. So, now it's done. Instead of using blue and green, I'm done with that. Everything now here times 1, I don't need to write 1. Looking at these boxed and circled for you, I could take a to the 4th out as a common factor. And from sine to the 4th phi and sine to the 2nd phi, I could take sine to the 2nd out. Let's do that. From the first one, I got sine squared left phi. From the second part is cosine squared phi, which this also equals to 1. Taking the square root of a to the 4, taking the square root of sine square, I'm not going to write plus minus, because sine phi is greater than or equal to 0 when phi changes from 0 to pi. So that simplifies to a squared sine phi. Okay, we did the main part. We could slow down on the integration that you could buy and follow without me slowing it down step by step. This is a cross product magnitude right there. Put it down here. dA means d phi d theta because those are my parameters. We have phi goes from 0 to pi and theta goes from 0 to 2 pi. I could take a square out. I could take d theta by itself because this has no theta in it. Integrating, finishing it, I have 4 pi a square as expected. Let's move on. I still have more. Surface area of the graph of a function. For the special case of a surface S with equation z equals f of xy, where x and y lies in D and f has continuous partial derivatives, we take x and y as parameters. This is very important and you need them for the coming sections, Stokes theorem and the divergence theorem. Here we go. We treat x and y as parameters. They are circled, they are highlighted. It's a big deal. Knowing what's the parameters is a big deal before you move on. So I have x equals x, y equals y because my x and y are the parameters, and z equals f of xy. This is a special case, but it's gonna save you a lot of time when you could use it. So I have r xy z is xi plus yj plus f of xy k. If you take your time and find the partial derivative with respect to x, that's a 1, that's a 0, that's df dx. With respect to y, you end up with the following. Doing the cross product, minus df dxi minus df dyj plus k. Thus we have the following. Taking the magnitude, that will be squared, that will be squared, no need for the minus signs, and that will give you 1. You want to keep this in mind from now on. What does that mean? The surface area for this special case becomes the following. That's a quick way to find the surface area when you could write z as a function of x and y. Of course, this applies differently if it's not z as a function of x and y, if it's y as a function of x and z. Same idea, it looks the same, and the one will be coming from the third part. So, let's move on. Example. Find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So we need to find the surface area the area of the part, okay, that's the surface area of this blue shape under the plane z equals 9 as it's mentioned. This z equals x squared plus y squared, and this z right here equals 9. We could refer to the surface, which is z equals x squared plus y squared, as a function of x and y, just like the previous special case concept. Setting z equals to z, this z equals to this surface, they're gonna meet at this circle. X squared plus y squared equals z, but now I want to make it equal to 9, and that means it's a circle with radius of 3 being up here at z equals 9 all the way up. Well, the projection of this will be down here, which is in gray. Therefore, the given surface lies above the disk D with the center at the origin and the radius 3. Now we use the formula because that is what we use for this concept right here. It's a special case. dz dx will be 2x, dz dy will be 2y. This one is right here. Finish the math. That's a 4x squared plus 4y squared. Well, x squared plus y squared is r squared if you use polar form, and by seeing this down here, that's a polar coordinates. So we have 1 plus 4r to the second, where r changes, r d theta for dA, of course. R changes from 0 to 3, and theta goes from 0 to 2 pi. Separate them because I can. This does not have a theta in it. And we have d theta by itself from 0 to 2 pi, which is 2 pi. Using u substitution, calling 1 plus 4r to the second as u. You need an 8 here. That's why 1/8 shows up. Skipping all the steps of calculations to save you some time. This is my final answer. That should do it, and I'll see you in the next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.